Children, let us continue the chapter Magnetic Effect of Electric Current. We have studied about the electric motor. So you know that an electric motor is a rotating device that converts electrical energy to mechanical energy. And you also know the principle used here. When a current carrying conductor is placed in a magnetic field such that the direction of current is perpendicular to the magnetic field, it experiences a force. This force causes the conductor to move. So here, by using the magnetic field and electric field, you will get a mechanical force. That electrical energy is converted into mechanical energy. This force causes the conductor to move, and motor converts electrical energy into mechanical energy. And now let us observe the one more situation. Let us imagine a situation in which a conductor is moving inside a magnetic field, or magnetic field is changing around a fixed conductor. What will happen? Scientist named Michael Faraday discovered that moving magnet can be used to generate electric current. Michael Faraday made an important breakthrough by discovering how a moving magnet can be used to generate electric current. So, let us perform an activity to observe this. Take a coil of wire AB having a large number of turns. Take a coil of wire AB having large number of turns. Connect the ends of the coil. Consider this is a coil, and connect the ends of the coil to a galvanometer. Observe, here is a galvanometer, and connect the end to the galvanometer. Here is a galvanometer. Connect the ends of the wire to the galvanometer. Take a strong magnet. Take a strong bar magnet and move its north pole towards the end B of the coil, and observe the deflection in the galvanometer. You will find the deflection in the needle of the galvanometer. Now let us perform the activity to show that how the relative motion between the coil and a magnet induces a current. Here, observe the activity. Take a coil wire AB having a large number of turns. Here is a coil AB. It is having a large number of turns. Connect the ends of the coil to a galvanometer. Here, connect the ends of the wire to the galvanometer, and take a strong bar magnet and move its north pole towards the end of the coil. Take a strong magnet, that is a bar magnet, and what you have to do here? Move its north pole towards the end B of the coil, and observe the galvanometer. There is a momentary deflection in the needle of the galvanometer. Initially, the galvanometer indicator was in this position, and the galvanometer deflects here. The needle of the galvanometer initially where it was? Initially it was here. When the magnet moves towards the coil, it deflects towards the right side of the galvanometer, right side of the original position. So there is a momentary deflection in the needle of the galvanometer to the right. This indicates the presence of current in the coil AB. Here you know that galvanometer is a device to detect the flow of electric current in the circuit. So the ends of the coil is connected to the galvanometer. So here when the bar magnet moves towards the coil, moves towards the end B, you will observe a deflection in the needle of the galvanometer, and this indicates the presence of current in the coil AB. The deflection becomes zero the moment of the motion of the magnet stops. If the movement of the magnet stops, then the deflection will be zero. Now withdraw the north pole of the magnet away from the coil. Now the galvanometer is deflected towards the left. Here, when the magnet moves away from the coil, withdraw the north pole of the magnet away from the coil, the galvanometer shows the deflection towards the left. Here, the deflection will be in this direction. It shows that the current is now set up in the direction opposite to the first. Means the direction of the flow of current changed as the magnet moves away from the coil. Place the magnet stationary at a point near to the coil, keeping its north pole towards the end B of the coil. We see that the galvanometer needle deflects towards the right when the coil is moved towards the north pole of the magnet. Similarly, the needle moves towards the left when the coil is moved away. When the coil is kept stationary with respect to the magnet, the deflection of the galvanometer drops to zero. Here, it shows that there is no current in the coil. So, when the magnet moves towards the coil, then there is a deflection. That is, deflection is towards this direction. When the magnet moves away from the coil, then also there is a deflection, that is in the opposite direction, in this direction. Children, observe the galvanometer. Positive end and negative end of the galvanometer are connected to the two ends of the, here these two are connected to the two ends of the coil. See here, and here the magnet is brought near the coil. See what happens in the galvanometer. Here it shows deflection when it moves towards and when it moves away from the coil. So here the deflection changes, the direction of the deflection changes when the coil moves towards and away from the coil. And as the movement becomes slow, the deflection also becomes slow. And if it is kept stationary, there will be no deflection. What do you conclude from this activity? Whether the magnet is moved towards or away from the coil, or the coil is moved towards or away from the magnet, the magnetic lines of force passing through the closed coil get changed. Here, magnetic lines of force linking with the coil get changed. This produces an induced potential difference in the coil, which in turn set up an induced current in the circuit. Here, potential difference is set up in the coil as the magnetic field linking with the coil changes. Magnetic lines of force linking with the coil changes. Current will be induced in the circuit. That is, this produces an induced potential difference in the coil, which in turn set up an induced current in the circuit. The current is indicated by the deflection in the galvanometer. The needle of the galvanometer shows the deflection. It indicates that there is a induced current in the coil due to the change in the magnetic field linking with this coil. When the coil and the magnet are both stationary, there is no deflection in the galvanometer. This indicates that when there is no change in the magnetic lines of force passing through the coil, no potential difference is induced in it. So, the changing magnetic field linking with the coil induces EMF, electromotive force or potential difference in the coil. But if they are stationary, if both the coil and magnet are stationary, then there is no potential difference is induced in it. So that is the conclusion we made here. In this activity, galvanometer is used. What is galvanometer? Galvanometer is an instrument that can detect the presence of a current in a circuit. Even though there is a small amount of current in the circuit, that small amount can be detected by using the galvanometer. It shows the deflection. The pointer remains at 0, that is at the center of the scale, for 0 current flowing through it. Here the pointer is at 0 means there is no current flowing through it. It can deflect either to the left or to the right of the 0 mark depending on the direction of current. Here the point can or the needle can move towards left or right, that is depending upon the direction of the flow of current. This is about the galvanometer. Children, we came to know that when the magnetic field linking with the coil changes, current will be induced in the circuit. Now, let us discuss about the production of induced current in one coil due to a change of current in the neighboring coil. If there is a change of current in the one coil, there is a production of induced current in the other coil. Children, to demonstrate the production of induced current in one coil due to a change of current in the neighboring coil, you do one activity. Take two different coils. Take two different coils of copper wire having large number of turns, say 50 and 100 turns. 50 and 100 turns. Insert them over a non-conducting cylindrical roll. It is a non-conducting cylindrical roll, and insert the copper wire through the non-conducting cylindrical roll. You can use thick paper roll also. Connect the coil 1 having large number of turns in series with a battery and a plug key. It is a coil with more number of turns, and connect the ends of this coil to the battery and a plug key. It is a battery and it is a plug key, and connect them in series. Also connect the other coil 2 with a galvanometer. Here the first coil is connected to the battery and plug key, and the second coil is connected to the galvanometer. Plug in the key. Here plug in the key, insert the plug. Observe the galvanometer which is connected to the second coil. Observe the galvanometer which is connected to the second coil. Is there a deflection in its needle? We will observe that the needle of the galvanometer instantly jumps to one side and just as quickly returns to 0. As soon as the key is inserted, what happens? The needle of the galvanometer instantly jumps to one side and just as quickly returns to 0, indicating a momentary current in coil 2. Disconnect the coil 1 from the battery. You will observe that the needle momentarily moves, but to the opposite direction. Here, disconnect the coil. Disconnect the coil means remove the key. Then what happens? The pointer moves instantly to the opposite direction, opposite side. It means that now the current flows in the opposite direction in coil 2. In this activity, we observe that as soon as the current in coil 1 reaches either a steady value or 0, the galvanometer in coil 2 shows no deflection. And what do you conclude from the observation here? Here, what do you conclude? We can conclude that a potential difference is produced in the coil 2 whenever the electric current through the coil 1 is changing. That is, changing means starting or stopping. Here you observe when the plug key is inserted, suddenly there is a deflection, and when the plug key is disconnected, it is removed, then also there is a sudden deflection. So you can conclude that potential difference is produced in the coil 2. Potential difference is produced in the coil 2 whenever the electric current through the coil 1 is changing, means it is starting or stopping. Coil 1 is called the primary coil. This coil 1 is called the primary coil, and coil 2 is called the secondary coil. As the current in the first coil changes, the magnetic field associated with it also changes. As the current in the first coil changes, what also changes? The magnetic field associated with also changes. Thus, the magnetic field lines around the secondary coil also changes. The magnetic field around the secondary coil also changes. Hence, the change in magnetic field lines associated with the secondary coil is the cause of induced current in it. As there is a change in the magnetic field linking with this coil, current will be induced through this coil. So, here there is a change in the electric current, and the current will be induced in the second coil due to the change of magnetic field linking with this coil. This process by which a changing magnetic field in a conductor induces a current in another conductor is called electromagnetic induction. The process by which a changing magnetic field in a conductor induces a current in another conductor is called electromagnetic induction. Here, the change as the current in the first coil changes, the magnetic field associated with it also changes. You know that current carrying conductor produces a magnetic field. As the current changes, magnetic field associated with that also changes. Thus, the magnetic field lines around the secondary coil also change. Hence, the change in magnetic field lines associated with the secondary coil is the cause of induced electric current in it. Here, the electric current is passed through the first coil. and changes will be in the first coil. Change of electric current is in the first coil. Change of magnetic field also in the first coil. But here this is a coil near to the first coil. So the magnetic field around this second coil also changes, which is the cause of induced electric current in it. So this process by which a changing magnetic field in a conductor induces a current in another conductor. Current in another conductor is called electromagnetic induction. Electromagnetic induction. Here in two ways the electric current is induced in the coil. One is by using the magnet and the coil. Here the magnet is moved towards and away from the coil. Then also there is a change in the magnetic field. Here also the magnetic field linking with the coil changes and induces the electric current in the coil. That is the one way of inducing the current in the coil. And the other way is having primary coil and secondary coil, changing the electric current in the primary coil, and that induces the electric current in the second coil. Here the magnetic field is created by using the electric current, and by changing the electric current the magnetic field linking with the second coil changes and induces the electric current in the coil 2. That is the second way. Normally we can induce current in a coil either by moving it in a magnetic field or by changing the magnetic field around it. That is by using magnet and a coil. The induced current is found to be the highest when the direction of motion of the coil is at right angles to the magnetic field. Here the magnetic field and coil, movement of the coil or movement of the magnet must be perpendicular to each other. Then only the induced current is found to be maximum. So we can use the rule which is named as Fleming's right hand rule to explain. So what is Fleming's right hand rule? That is, stretch the thumb, forefinger and middle finger of right hand so that they are perpendicular to each other. If the forefinger indicates the direction of the magnetic field and the thumb shows the direction of motion of conductor, then the middle finger will show the direction of induced current. Here, what is Fleming's right hand rule? Stretch the thumb, forefinger and middle finger of right hand so that they are perpendicular to each other. If the forefinger indicates the direction of the magnetic field and the thumb shows the direction of motion of the conductor, then the middle finger will show the direction of induced current. See here, motion of the conductor, magnetic field and induced current. They are perpendicular to each other. Children, you write, what is electromagnetic induction? What is electromagnetic induction? The process by which a changing magnetic field in a conductor induces a current in another conductor is called electromagnetic induction. You write that the process by which a changing magnetic field in a conductor induces a current in another conductor is called electromagnetic induction. Children, next you write the Fleming's right hand rule, which is also called as dynamo rule. Fleming's right hand rule, which is also called dynamo rule. Write that stretch the thumb, forefinger and middle finger of a right hand so that they are perpendicular to each other. If the forefinger indicates the direction of the magnetic field, thumb shows the direction of the motion of the conductor then the central finger points in the direction of current in the conductor.